Oh yeah, I can't.
I mean, this is ill time, but I think I really need to go to the bathroom.
Okay, that's fine. If you got time to mingo, mingo. Otherwise, it's fine. I don't want to. I want to keep this bigger or in this presentation so I can change colors like I did last time. I think for some of you that helps to know where the units are coming from and what thing is associated with what. So it's not quite as good of a view, but I think it's beneficial to have it like that. All right. So today we're going to talk about light and energy and how light can produce actual energy. Okay. So we talked about Max Planck. He is a German, looks like that should be a capital G, sorry. He was a German physicist in the 1900s, and he analyzed data that came off of radiation from heated substances, kind of like your stovetop. If you've got an electric stove with the coils on it that glows, even the glass top ones, it kind of glows from the heat. And he realized that atoms and molecules only emit energies in certain quantities or quanti. And he used the word quantum to mean that small amount. And we talked last week about a photon. The energy of that magnetic or electromagnetic radiation is always an integer in multiples of HV. And we need to talk about what H and this V is. It's not really V, it's what they called that last week, the Greeks. Nu. Yep. And it stands for frequency. And then he set up his theories from there. Okay. So about 5 years later, Einstein, another capital G issue here for Germany. I don't know why these countries are not getting capitalized. Okay. You've all heard of Einstein. He used that to study the photoelectric effect, and he described where these electrons were getting ejected from a surface. This is how like solar energy works with the solar cells that they have. You've seen these solar farms that they're setting up. If you've ever had a solar powered calculator, it's the same principle. It's light hits it and it causes these electrons to pop off. And those electrons are essentially electricity. They just capture them and then use them for electricity. Okay. So he said that the beam of light was really just particles of light, which we call photons. It's equal to this H, which is Planck's constant. It's another constant. Last week we learned one constant, which was the speed of light. Now we're learning another one. And then it's equal to Planck's constant times the frequency. And they were able to kind of come to a conclusion that light is not just particles, but it also has waves associated with it as well. And we can see that light, when it's split, appears to be a rainbow. You guys have probably played with prisms before and you've seen that. And then you can also have different gases in a discharge tube, which we're going to look at tomorrow, which is going to give you a specific color. Okay. Hydrogen, for example, when it is split out, you only get 4 stripes, and that's because it only has 1 electron. And essentially what's happening is you are sending in that light is coming out. It's got 4 different stripes if we really analyze it. So we can send it through a prism and then get 4 different stripes. And I'm going to have these spectroscopes that you're going to use tomorrow to be able to look at different elements. I'm going to put different ones in. Each different element has a different, they call this a fingerprint.
Isn't this how they found the chemical makeup of the sun?
Yep, exactly. Yeah. So what they can do is they can look off at like distant stars and planets and stuff, and they can look and see what stripes are given off. And from that, they know the fingerprint of each different element, they can match them up and figure out what elements exist on those, like the sun and other stars. So it's kind of interesting. Bohr then presented a theory. He said that, and we talked about his atom last unit in unit 4. He said that electrons are going to travel around in specific orbits, and each electron absorbs energy from, and it's going to bump up an energy level, but it's not stable, so then it falls back down and gives off energy in the form of light or other radiation, actually. Did I go too far? I did. So when the electron drops back down to what's called its ground state, it's going to give off the light. And we can use this equation, E equals Planck's constant times the speed of light divided by wavelength, to figure out what the frequency is. So essentially what's happening is when these atoms get excited, and they can get excited in several different ways. One thing that we can do is we can push electricity through them, like in the form of a light bulb, okay? The electrons get all excited, and they climb up levels beyond where they would normally be. But they're really unstable. They can't stay there, and so they fall back down, and when they fall back down, they give off light. And depending on how far they fall, determines what type of light they're going to give off. So if they don't fall very far, they're going to give off red light. If they fall a big distance, they're going to give off violet. So that corresponds to it. And each atom has a specific distance between the nucleus and these levels. And so each atom gives off just a slightly different color when it gets excited and comes back down. Yeah.
Falling would be like the top to a bottom of a wave.
No, well, I mean, they're gonna essentially get excited. So if normally the electron is here, right? It gets excited and it climbs up these electron levels, but it's unstable. It can't stay there. Okay, it's kind of like me on top of a ladder. I can't stay there for a long period of time. Eventually, I have to come back down to the ground. And that's what happens here. These give off light, and depending on where they fall back down to, so for example, if it falls back down to here, it's going to give off one wavelength of light. If it falls back down to here, it's going to give off another wavelength of light. And so it'll come out a different color.
Yeah, so the amount it falls determines like the distance between the top and the bottom of the wave.
Mm-hmm.
Okay.
Not the top and the bottom. That's the amplitude. It's going to change the, so it might be this versus, so it's going to change the wavelength. So the distance between here to here versus here to here. When we look at hydrogen, that's called the Balmer series. And hydrogen's an easy one because it's only got one electron that's popping around. You keep climbing up, you get more electrons that are moving up and down, and so you give off a lot more wavelengths of light. All right. These are just what those are called as far as giving off different light series. All right. So now we're back to here. I'm just going to real quickly take you back in the notes to this chart. Okay. I just want to briefly talk to you about a couple different things on here. This is where we introduced you to the different variables and constants and what they're measured in. Okay. So we talked about wavelength last week. We talked about frequency last week. Now, and we talked about speed of light last week. Now we're going to talk about these other two here. So we have energy. Energy is measured in units called joules. And then we've got Planck's constant. So this is another constant where it is always going to be this number. So if you see H, you write that down for your number. You don't have to think about it. You don't have, this number will be given, all of this stuff, well, yeah, the constants, all of this stuff here will be given to you on your test. Everything that I've circled there. Okay. So all of this will be given to you on your test. You don't have to memorize any of these equations or values. Okay. But H is always going to be this number. Because H is this number, sometimes we need to get things into joules. And typically, a lot of times, things will be given in kilojoules. And 1 kilojoule equals 1,000 joules. So you might want to have that in your dimensional analysis pocketbook, I guess. You can call it wallet, whatever. Yay? All right. All right, so I want to go back to today's notes then. See if I can find. There. Okay. So we are calculating the energy of a gamma ray photon. We are given frequency. So we've got 3 equations now at our disposal. We have energy equals Planck's constant times frequency. We have energy equals Planck's constant times the speed of light over wavelength. And we have the speed of light equals our wavelength. Wavelength times our frequency. So those are our 3 equations that we're using for this chapter. All right, so which one of these do I want to use? 1, 2, or 3?
Energy, so I would assume the first one.
Yeah.
Yep, because we don't have wavelength, we've got frequency. So we want to use the first one. All right. So energy is going to equal Planck's constant times frequency. Yay? All right. So energy is going to equal Planck's constant, which is 6.626 times 10 to the negative 34. Haven't used this in a few weeks. Yep, 34. And that's joules times seconds. Now, remember we can change hertz into what?
1 over seconds.
1 over seconds, right. So we're going to change this to 1 over seconds. So I'm going to multiply this by 5.02 times 10 to the 20th, 1 over seconds. Everybody go with that? All right, my seconds then are going to cancel, and that's going to leave me with energy in what unit? Joules, and we said that that's what we wanted energy in, right? Okay. All right, so see if you can get the answer to come up in your calculator. We're still playing with our calculators, making sure we know how to use them. Make sure you get that answer. Did that come out for you? Right. You don't use that piece of junk. That's a bad calculator. That's just almost impossible to work with. I understand, but I paid $1 for that at the Dollar Tree. Okay, it's painful. When is yours coming in? Check your Amazon shipping.
She ordered one, yeah. There's a graphic one from there.
Well, hopefully she got you that one. Yep, that one is here. And then 20. Oh, no. Crap. Nice thing about this. There we go. Now we're going to multiply, yep, and then multiply that times. Okay. There you go. Now you got the right answer. Anybody not get this? Let me come by and help you.
No, I got the answer. I'm just confused on where you got 6.626 times.
That's what H is. Anytime you see H, remember I was showing you that chart. We went through that. Oh, shoot. What is happening with this thing? Okay. Remember when I was showing you this chart a few minutes ago? I said Planck's constant is always that number. Good. That's in your 5-1 notes. That chart. All right, here is the next one. We are given, they gave you Planck's constant in the problem. They gave us a wavelength this time instead of frequency. So what am I going to use here? There's a lot of stuff on this screen. Which equation am I going to use? Yep. Number two, right. Okay. So I'm going to use E equals H what do I want to see in? What do I want to see in? Can I do a highlighter that's not, it's black. Let's do a black highlighter. Oh, that doesn't work well, does it? Maybe we don't want to use that. Oh, there we go. I can do thickness there. Well, let me give you a, I want to do black. There's C. Okay. And then this guy will be our speed of light for this one. Or not speed of light, our wavelength. Okay, good? Does that work for everybody? Okay. All right, so start putting in our values here. Planck's constant again, same number every time, 6.626 times 10 to the negative 34. That is joules seconds. I'm then going to put in my speed of light. My speed of light is 3.00 times 10 to the 8, and that's meters per second. Kind of obnoxious, isn't it? And then I'm going to put in my wavelength. Now, they gave me several different things here. Which one do I want to use for my wavelength? Which one of these things do I want to use here? There's a whole bunch going on there. Yep.
I don't have the answer, but why isn't it meter for the back to C? Why isn't it meters per second?
Why is it meters per second?
Why isn't it?
For speed of light?
Yeah.
Speed of light is meters per second. Meters over seconds. All right. Getting back to frequency. What number do I want to use up here?
2.
That's the equation I'm using.
Sorry.
Yep.
Yeah.
Which frequency do I want to use? Do I want to use this guy?
Meters.
The meters, right. We want to use this one because we want to be able to cancel out these meters when we're done. Okay? All right, so I'm going to put that guy. He goes on the bottom. So he is 5.25 times 10 to the minus 7 meters. All right. Now we're going to go and we're going to start canceling some stuff out. So my meters will cancel here, and my seconds are going to cancel here. That's going to leave me with an answer in what? Joules. We are measuring energy. Energy should come out in joules. So see if you can get the right answer on your calculator. You're having to enter in 3 different numbers for this guy, so make sure that you're getting it to come out, because this is a lot to get into that calculator. If you're not, call me over and let me help you out, please. I'm down on my knees begging you right now. Can you visualize that?
Not really.
Can you visualize it now?
Yeah.
Okay. Anybody not able to get that to come up? Anybody not able, ready to move on?
How did you get the 9?
9.
It's for 3.79.
3.79 here.
Yes. Well, I stand the 7. I got 3.577. I'm wondering if I did something wrong.
Did you remember to? Yeah, you got all kinds of. You're getting to the negative 49th on top of it all.
Oh, this is for the next problem. I was talking about this is the answer that I got for this one. I have the right exponent. It says with 3, but I don't have the right decimal.
So you typed in 6.26 here instead of 6.626.
6.
See right there?
6.26.
Yeah, it should be 6.626.
Okay. Thank you.
All right. We are going to stretch you for the next one. You ready? We're actually going to talk about moles in the next one. So a mole is just a counting unit, you guys. It's like a dozen. A dozen is how many? 12. A mole is 6.02 times 10 to the 23rd of something. It could be atoms, it could be molecules, it could be strands of hair, it could be sands of grain or grains of sand on the beach. Okay, it just means that that's a mole of that material. Okay, so here we are given a certain energy. This is a single photon, and this is our energy. The first part of this, they want us to answer what is the frequency of this UV radiation. So I want to figure out frequency, and I'm given energy. Which equation am I going to use? Energy, if I have frequency, what am I going to use?
Oh.
First one, right. Okay. So that is energy equals Planck's constant times the frequency. I need to rearrange that to solve for frequency. So I'm going to take, and I'm going to have my frequency equal to what? Energy over Planck's constant. So see if you can sub in your values for that and come up with the correct answer for it. Compare it with the person you sit next to, see if you came up with the right answer. Then see if you can solve for wavelength. I know. No? I put my hand in right here. Start burning in another 10 minutes. And as the acid eats away at the first layer of skin.
That's way down. Avoid that.
All right, let's go here. All right, so you should have gotten your frequency equals our energy, which was given in the problem here, 6.056 times 10 to the minus 16, and that's joules over. And now I need to put Planck's constant in. 6.626 times 10 to the minus 34, and that's joules seconds. And my joules will cancel out. That's going to leave my answer in units of what?
Seconds.
Not seconds. 1 over seconds, right. Okay. And I ended up with 9.14 times 10 to the 17th. That's 1 over seconds. Everybody good with that? All right. Now, the next one, you can choose which way you want to do it. You can either use this equation or this equation. With this one, you'll have fewer things to type in, so that's the one that I'm going to go with. Are you okay if I rearrange this right away?
Yes.
Yeah.
Okay, so I'm going to get wavelength by itself. So my wavelength is going to equal my speed of light over the frequency. And we're grabbing the frequency from here and bringing it up. Make sense? All right. So my wavelength then is going to equal my speed of light over my frequency. And again, I'm just bringing that up from this previous problem down here. 9.14 times 10 to the 17th. And my units are 1 over seconds. So the seconds are going to go on the opposite side of the number. So my seconds are going to cancel out. And that's going to leave me with units of meters. So I ended up with 3.28 times 10 to the negative 10 meters. All right, everybody cool with that before we jump into dimensional analysis? I know you just love that, don't you? All right, I'm going to erase this. So anybody not ready for me to erase this? You good, Monica? Everybody good? Yes. Yep, I'm going to. I just need some board space. I just want to make sure that you're okay with A and B before I erase it, though. I just don't have enough room on here to be able to do what I need to do. All right, everybody good? All right. This is all going to go bye-bye then. So for C, they want to know the energy of 1 mole of these photons. And they want that in kilojoules per mole. Okay? So first of all, we need to know what a mole is. Okay, so this is another conversion factor you need to have in your wallet of different conversion factors. Okay, so 1 mole equals 6.02 times 10 to the 23rd anything. It doesn't matter. It's just like a dozen. It could be a dozen paper clips or it could be a dozen donuts. Okay, it is a counting unit. In this case, it's going to be photons. All right. The abbreviation for mole, M-O-L-E, is M-O-L. It doesn't save you much. I know. All right. So I'm going to start out with my joules here. We are practicing our dimensional analysis. 6.056 times 10 to the minus 16 joules. I just rewrote down the quantity that they gave me. All right. I need to then get these joules into, and this is per 1 photon. So we have that many joules in every photon. Everybody follow me so far? You doing okay with this? All right. I need to get joules into kilojoules. What do I do?
It's 1,000 joules equals.
Right? So where do joules go, on the top or the bottom?
Bottom.
Bottom. So I'm going to put joules down here and I'm going to put kilojoules up here. And for every one of these, I have 1,000 of these. All right. So now I have it in kilojoules per photon. I need to get rid of photons. Where do I put the photons? On the top. And I'm going to take that into moles. Okay. I know for every 1 mole, I have 6.02 times 10 to the 23rd photons. See if you can do that math in your calculator and come up with the correct answer. You should come up with 3.65 times 10 to the 5th kilojoules per mole. Photons cancel, joules cancel. Are you using one of those janky calculators too? Know how to use that one? So type in your 6.056. You're going to hit the second key, and that key right there says E. Now type in negative 16. You're going to multiply that times 6.02. Second, E 23. Divide. You can hit to the 5,000. Right? Anybody not able to get that to come up on their calculator? It's just not in scientific notation. If you move this 5 spots, it's going to. Yeah, it may not come up in scientific notation, but you should be comfortable with taking a number and getting it in and out of scientific notation. All right? Yay? Nay?
So we should write it in scientific notation.
You don't have to. I'm just saying that if I have an answer on an answer key that's in scientific notation, you should be comfortable being able to say, oh, that's the same number. Does that make sense? You need to be able to slide in and out of scientific notation. All right, so I do. We're calculating wavelength and we're given energy. So which equation, 1, 2, or 3, am I going to use today?
No, sorry, 2.
2. I've given wavelength and I want to go, I've given energy and I want to go into wavelength. So my energy equals Planck's constant times the speed of light over my wavelength. I need to get wavelength by itself. So I'm going to multiply both sides by wavelength. So my wavelength is going to come over here then. I multiply both sides by it. It'll cancel from here. And now what do I need to do?
Divide by E.
Oh yeah, that should be in a different color though. This guy should be in a different color. So I want to divide both sides by E. So if I divide this side by E and this side by E, that's going to get wavelength by itself. All right, so I've rearranged my equation. I think it's easier to rearrange the equation with variables than it is with numbers because it's a lot less writing for one thing. Okay, all right, so I'm going to continue here. I'm going to have my wavelength equal to Planck's constant times the speed of light divided by energy. My energy they had in joules, so we're good to go with that. We don't have to convert it into anything. And that's going to be joules. All right. Joules will cancel. Seconds will cancel. And that's going to leave me with meters. I'm measuring wavelength, so that's good because length is measured in meters. So my wavelength then, when I do my math, and you want to make sure that your things are coming out right on your calculator, is 1.09 times 10 to the -6, and that is meters. Did you get that to come out on your calculator okay?
Yes.
All right. So tonight you're going to do the WeDo. You watch the video on that if you need to with the QR code scanner. And the rest of 5.2 is due tomorrow. We have a lab tomorrow, so just kind of be aware that that's coming up, okay?
Yeah.
And then, honey, I think it might be time for you to have a new folder. What, honey?
Can you do that up a little longer?
Yep.
I